All right. Yeah, it's going to be a little shaky, so sorry about that. But I've done this once for my algebra class, so hopefully I've gotten over the weirdness of this. But so what I want to do is I want to make a very focused video, maybe 10-15 minutes. We'll see how it comes out. A couple examples of central limit theorem. This is from chapter 7. So this is where we were talking about, depending on which class you're in, alternate universe Florida or an island somewhere where we had the ages of people and it took one person at a time. And then what happens if we take 20, whatever I said, 20 people at a time, and you end up with something that's approximately normal. So the central limit theorem says the larger n gets, the more normal the distribution of sample means gets. So if I take a bunch of sample means, the larger my sample size gets, if I plot each of those means, they'll become more and more normal. And the neat thing is, if n is greater than 30, it is approximately normal no matter what it looked like to begin with. That's really cool. Why? Because I have a sheet of all the answers that would have been really smart for me to actually get a sheet before I started this, but too bad. The z-score chart, it's a sheet of all the answers to anything as long as the distribution I'm working with is normally distributed. Then I can answer any probability question within that distribution. So let me get one started, and then hopefully as I'm working on it, I'll remember where there's a z-score chart I can get to real quick, but we'll see if that happens. Two more things. Central limit theorem says this, and of course the other two things. One thing we did talk about, the standard deviation changes like this. So as my sample gets larger, it should get skinnier, because now it should be even less likely to be very far away from the mean. So if I get my sample to be really, really big, everything should be really close to the actual mean. It should be really hard to get a large sample that has an average that's really far away from the real average. That should be really unlikely. The other thing I didn't really say explicitly is the mean stays the same. So I can't change the mean of a population if I do it one person at a time versus two people at a time. The average, whatever it is, should stay the same. That's all this says. Okay, so let's try a problem out. Yeah. So let's say I have I'm given a distribution with the mean is 30 and the standard deviation is 11.29. Why? Why, Jeff? I don't know. And let's say I take a sample n equal to 38. I like it. Okay. Now, why would I be allowed? So if I ask a question like, what's the probability that my sample mean is less than 31? Let's say that's the question, right? What's that probability? You might start jumping right into it, but you cannot use the chart unless I know I have a normal distribution. And in this case, it doesn't say a damn thing about being normal, but n is greater than 30. So central limit theorem says, go for it, right? So this distribution is going to look like this now. It's going to have the mean stays the same, right? And here's my 31. And I want the probability is less than 31. But before I go to make a z-score, I'm working with samples of 38. I cannot use this. This standard deviation is for individuals. I need the one that works for groups of 38. So I've got to change my standard deviation. So it was 11.29. So when I divide it by the square root of 38, here's the other thing. Calculator helps. I'm not bad. I would estimate this to be 1.8. Let's see how close I get. Oh, the suspense. All right, sorry. 1.831. Beep. Become a 3-1. Thank you very much. All right. That is the one step that we did not have to do before because n was always 1 for us in chapter 6. Now I could be taking a sample of whatever size, and I'm going to have to change the standard deviation before I go make z-scores. Now we do exactly what we did before. That's the only change in chapter 7 is the standard deviation becomes this. So now, let me see. I think my green's working. Don't even know this is going to show up on the camera differently. If I go to make a z-score, my data point minus the mean divided by the appropriate spread, which is this, become an 831. 831. Okay. And this green one's not terrible. So when I do 1 divided by 1.831, pop. No, yes. Okay, good. Okay. I get 0.55. So the z-score is 0.55. So if I look that up on the z-score chart, I'm going to get the answer. And do I have a z-score? Holy crap. All right, Jeff's a lucky boy. So let's see, the z-score chart. Let me see if I can make this work. Z-score chart. I want 0.55. So 0.55 looks to be 0.7088. That's not too bad. That works all right. 0.7088 is what I think I said. So that's going to be the answer. 0.7088. Just over 70 or just under 71% chance to take a sample and have the mean be less than 31. It makes sense. The actual mean's 30 for everything. So if I take 38, they should be close to the real mean. So there's a large chunk of them that'll be less than 31. Not as many of them above 31. Kind of makes sense, hopefully. All right, let me see what time I'm at. Make this a decent... Yeah, let's do one more. I think I can see everything right. Yes. There's Homer Simpson capturing how we all feel. Thank you, Homer. Oh! All right. Nice thing is I don't have to wait too long. You can just pause the video if you need to see all that business. All right, let's try one more. So let's say given a normal, there we go, distribution with mean of 1.98 and standard deviation of 0.71. Let's just make it 1.7. I don't know why. All right, so let's say I want to know the probability that x is greater than 2. Yeah, let's do this. I like this. Let's do 2 of these. Why can I not do this? I can't do this. Because I didn't... Oh, of course I can do it. That's not my point. Should I stop this? No. You guys can deal with this, right? All right. I can do this because I did say it's normally distributed. So I'm able to do this problem. This is a chapter 6 problem, right? So I've got a mean of 1.98. I know the probability that greater than 2. I make a z-score. My score minus the mean divided by the standard deviation. Of course, I can use this one because this is just a single value. I haven't taken a sample. So then this z-score is going to be, what are you going to guess, Jeff? 0.13. Let's see if that's right. 0.12, I can live with that, right? You guys can double check me. Yes, okay. And so if I look at 0.12, and we've done this enough that you can find 0.12, it says 5478. That, of course, is not the answer. Oh my gosh, my memory only goes so far. What did I say? 0.5478. So to get the correct answer, I got to do 1 minus that. 4522. Okay, so that's chapter 6. Here would be the new one. If we take a sample of n equal to, let's do 10, what's the probability that the sample mean will be greater than 2? So, a couple things. How do I know when I have to use this formula? Well, I have to use this formula when I take a sample and I ask about the sample mean, because I need the standard deviation that works for sample means. This standard deviation works for individual values. So when do I do this? When I take a sample and I'm asked about the sample mean. Those are the two triggers to know when to do this. Once I get this new standard deviation that works for this, I do all the same work. I just don't put a 0.17 here. I put whatever the hell I'm going to get here. That's going to be the appropriate spread. All right, so let's see what we get. 0.17 divided by the square root of 10. I don't know what that's going to be. I got to give it a try. 0.048. I don't know. Let's see. Oh, scheisse. There it is, Jeff. 0.054. Okay, I can live with that. That's not too bad. All right, 0.054. So now I just attack this fresh. This is the one new step I never had to do before because we never took samples before, but now we do. I change that. Now I've got my same picture. The mean is 1.98. I'm curious about greater than 2. Same stuff. Now when I go to make a z-score though, I use the appropriate standard deviation, which is 0.054. And that is going to be, bam, bam, I don't know, 0.36. Let's see. 0.37. All right. I got to show off every now and again. So that's 0.37. So when I look that up, again, it's not going to be the answer because I need that side. But let's see, 0.37 looks to be 0.6443. Double check that. Yes, okay. And then I have to do 1 minus. I'll get 0.3557. Shapoo! So about almost a 36% chance to pick 10 things out of this distribution, and their average is bigger than 2. Notice that it's a higher chance to get 1 thing greater than 2 than it is to get 10 things greater than 2, and that should make complete sense. The average of everything is 1.98, so a sample of 10 should be closer to 2 than any individual would. There should be less chance to get above 2. I'm hoping that makes sense. All right, I think that's about the size of a video I wanted to make. Yeah, it's perfect. Just below 15 minutes. So I'm going to chop it. That's the end.